Hello and welcome to lecture 4 on half-lives. All right, in the last lecture we talked about exponential functions, and today we're going to talk about a particular application of exponential functions that's going to show up a lot in this class, and that's exponential growth and decay. All right, so in the last lecture we introduced an exponential function as anything that has a particular base raised to the exponent that has the independent variable in it. This is called the exponent. And then we talked about whether if r is greater than 0 and hence that exponent is positive, that this is growth. When r is less than 0, that this is decay. So you have a y-intercept of 1, and then you're either decaying or you're growing from that y-intercept. Today we're going to change this exponential function a little bit, and we're going to write it according to this equation here, where we have n time t is equal to n0 e to the rt. So what this is, another way of interpreting this is the population size at time t. So our independent variable is time, and our dependent variable is population size. And we have this n0 here, which is the population size at time 0. And then we have our exponential growth term here, which is e to the rt. So in general, any exponential function, the domain of that exponential function can be anything in the real numbers. But now we're starting to get into a world where we're making biological functions out of these functions that we mentioned in the previous 2 lectures. And so we know that time has to be positive. You can't really have negative time. And so if we only have positive time, then our domain of our function, the set of all values of that independent variable t that we have, can only be positive. So we're going to only think about time increasing from 0. Similarly, a population size, we wouldn't make sense to have a negative population size, so our population size is going to have a range of the positive real numbers. All right, so r here in this particular iteration of the exponential function is known as the growth rate. If r is less than 0, then it is actually a decay rate is less than 0. All right, so we can either have growth or decay. And since this term here has a y-intercept of 1, and we're multiplying that y-intercept by n0, our new y-intercept is actually going to be n0. So consider these 2 functions here. This blue function, g of t, is equal to n0 of 1 e to the 0.5 times t. So this is our y-intercept. If we plug in t equals 0, we get out a 1. So we have a y-intercept of 1 here. And then our second function, f of t, is equal to 100 e to the minus 1 times t. Now, this term here has a y-intercept of 1. If we plug in t equals 0 and we get 1, we have 1 times 100, so we have a new y-intercept of 100. All right, and then because this is negative, we have a decaying exponential, and because this is positive, we have a growing exponential. All right, so this model here that I've introduced is known as exponential growth, and in particular, it is a type of exponential growth known as continuous time exponential growth. And so continuous time is a good way of describing things that reproduce, populations that reproduce continuously, like bacteria or humans. Babies can be born at any minute of any day. Now, not all biological populations are well described by this. Oftentimes plants or some insects reproduce on a very scheduled regime, where the insects are born at a particular time of year, or the plants can only set seed at a particular time of year. And in this case, we might actually want an alternative to continuous time, where our domain is not all the positive real numbers, but is instead a set of integers positive integers, z plus, that describes the year or the month that you're reproducing in. So an alternative to this continuous time exponential growth is something known as discrete time growth. And here we have a domain of the positive z. So the positive integers. And in this case, we have a base of r raised to the t, and this is our population size at time 0. If we plug in t equals 0, anything to the 0th is 1, so at that point this is 1, and we end up with that n0 as our pop size at t equals 0. And so it has the same interpretation as before. And this is the extent to which the population grows each time step. So each year or each day, whatever t represents in this case. Okay. And so if r is greater than 1, then our population is going to get bigger over time. If r is less than 1, then the population is going to shrink. So in particular, consider the case when r is equal to 2. Then that means that every generation, or whatever t represents, that the population is going to double. So if t is every year, and those represent our generations, then as we go from f of t is equal to 10, our initial population size, times 1.5 to the t, then every generation our population is going to increase by 1.5 times. So we're gonna increase the value by 1.5 times. So there's 1, there's another half. Here's 1, here's another half. All right. Similarly, if we have g of t, and we have our initial population size of 500, and we have a value of r that is less than 1, then the population is going to shrink every generation, and in particular, in this case, it's going to get half as small every generation. So we're going to take half of the size. So we start with 500, and in the next generation, we end up with 250, and the generation after that, we end up with 125, and so forth. All right. So that is discrete time growth versus continuous time growth. And which option makes sense depends on the biological problem that we're dealing with. If we're dealing with populations that reproduce continuously and have these overlapping generations, then we're going to want to use a continuous time model of population growth. If things reproduce on a schedule, for example, they set seed at a particular time or a particular season, or they have to all cluster in the ocean, for example, and release eggs and sperm into a water environment in order to reproduce, then they have this seasonal scheduled reproduction event. And in this case, it's often much more realistic to describe the populations in terms of generations. And so we might want a discrete time model of population growth. All right. So in particular, today we're going to talk about continuous time models of growth and decay, and we're going to define a quantity known as half-life. So to think about half-life, consider a population that is decaying. So we have our initial population size n0, and we have a negative exponent minus r. So we start at n0 of 50, for example, and we're letting that population decay over time. The half-life is asking the question, how long do I have to wait? What is the amount of time that I have to wait until the population is half of its original size? So if we start at 50, how long does it take me to get to 25? So what is this special time t at which I'm at 25? So we have that our model is n of t is equal to n0 e to the minus r times t. Now, we want to know when is n of t, at what time is that half of the initial population size? So this is what we're asking. What is t of 1/2? This is our focal thing that we're trying to solve for. Well, how do we solve for this? You can use those exponential rules that we learned in the previous lecture, but before that we have to do a little bit of algebra. Let's divide both sides by n0. This lets us cancel, and we have 1/2 is equal to e to the rt, our half-life. Now, how do we get rid of that e? Well, remember that e's and logarithms are opposite of each other, so we can take the natural log of both sides. This lets us write this as natural log of 1/2, and then we can cancel the natural log and the e is equal to r t 1/2. Dividing both sides by r, we have that t 1/2 is equal to the natural log of 1/2 divided by r. So this is our half-life. Okay, so let's work out a particular example. Let's extend this to the case where we have not the half-life, but the 1/5 life. How long do we have to wait until the population is at 1/5 its original size? So this is going to follow the same rules that we had before. We had n of t is equal to some initial population size, e to the r, and then the 1/5 life is what we're asking. And this is the amount of time that corresponds to 1/5 of our initial condition. So that's what n of t is. We can divide both sides by n0 to get rid of that. And we end up with e to the r. Our 1/5 life is equal to 1/5 over here. How do we isolate that t to the 1/5 life here? Well, we have to take the natural log of both sides, and we end up with the e and the natural log canceling. So we have our 1/5 life is equal to the natural log of 1/5, which means that t is equal to So we can have a half-life, which you may have heard of before, or we could have a 1/5 life or any other fraction. So if the population is decaying, we could ask, how long does it take to get to 1/10 the initial size or 1/3 the initial size? All right. The same principle applies if the population is growing and not shrinking, but instead of talking about a half-life, we have to talk about a doubling time, because it's never going to reach 1/2 the size, but it can reach twice the size. So in this case, we're asking, how long does it take until I double in my initial size? So if I start at 5, how long does it take until I get to 10? What is that special t? So in this case, I have n is equal to 2 times the initial value is equal to n0 e. Now notice that the r here is positive because it's growing. Once again, we can cancel the n0s on both sides, and we just end up with 2 is equal to the r times t. This proceeds just like before, where we take the natural log of both sides, and we have ln of 2 is equal to r. T dividing by r gives us this. So t is equal to, I'll put a little subscript 2 here to denote the doubling time. And that is our doubling time for this question. All right, so the same principle applies, that just like you can have a half-life and a 1/5 life, you can have the amount of time until your population grows by, let's see, what did I do here? Tripled in size. So we could have a t3 here. How long does it take us to go from 5 to 15? Try to do this on your own. So pause this video now and try to work out the amount of time it takes for this function to triple in size. All right, so welcome back. Let's work this out. We have that our population size, how long does it take it to triple in size from the initial value? Let's divide both by n0. So we have 3 e to the r t. Now let's take the natural log of both sides. and divide by r. All right, so I have specific values for what r is in this example. For example, I have the value of r is equal to 0.3, so that we have that the tripling time is equal to the natural log of 3 divided by 0.3. And so this is going to be exactly the same principle you're going to have to use in order to evaluate the self-study question. So test yourself on this, and I'll see you in class.